So, hello and welcome everybody to our second part of the simulation. Welcome back. Okay, so before I start with the presentation, oh, 1 second, here it is. Let's actually look to the second part. The last time we did the first part. Now the second part is actually starts with the timing model and file IO. So, but now let's actually look to the VHDL simulation for the webinar. And that's actually just to run through it. This was actually the first part, and just to again to give you the idea where we are. So now we are talking about, if this is the overall VHDL design flow, we are talking about the actually the simulation part and defining and doing test benches. So I hope it will be good enough, because I have the feeling that the internet connection today is not very good. I don't know why, because I see some kind of latency during my presentation. I hope you still will be able to follow this. So that's actually the area we're going to talk about: the simulation and the test benches and all the stuff around this. Okay, now actually let me just interrupt this and go right to our part. We finished the last time. So the last time we talk about all the processes and how to run the stimuli and how to actually define this. Now the second part, and there are some examples, but now let me go to the second part. So this second part actually starts right here, and let me go sorry, a little bit too fast. Yeah, let me go this way. So this is the timing model. Okay, so this means and that's actually the beginning of the second part, timing model. So what is a timing model? What we do have in order to model exon components, what we do have, you do have so-called timing, VHDL timing model. So what is all about this VHDL timing model? Let me just call, here we go, my notebook here, just to show you the idea of a timing model. It's I don't know, everything is a little bit slow today. Something happened here in the internet connection in Europe. I don't know why. Okay. So something happened here. 1 second, please. Well, maybe, but I can actually wait a little bit and spend the time to explain it maybe here. So what is how do we need a timing model? For example, if this is my FPGA right here, what happened with something happened with the complete with the delay. So sorry about this, but we do have some problems here, and I don't really know what is the effect here. So if this is my FPGA right here, then so then they should be able to model. It is my notebook finally there. So I don't really know what happened here. So what, again, what is the point? And I hope I can draw it actually somehow here. So this means in order to model some external components, okay, which are maybe connected to my FPGA, I need to define some timing. I need to be able to define some timing behavior, maybe of the input component and maybe of a component which is just connected to the output. So this would be maybe an output component. Okay. So, and in order to do this, VHDL does offer me a timing model. So if I just go, I think something happened. 1 second, please. 1 second. What's this? And so now, and VHDL offers a two timing model for me, and I think now I can do it a little bit delayed, so sorry about this. So this means I'm able to assign some timing information to a model, to a component like the input buffer or whatever. Again, this is not what you can use for synthesis, but this is something we should use for the simulation. So this means, but we have two kinds of different delay models here. One is called inertial delay model. What is this? This means we are able to model a component like a buffer, but if we use inertial, keyword inertial, which is a default, so we can also skip it. We don't have to do it, but because it's a default. But for example, X is inertial B after 2 nanoseconds. If we use this, this means that this buffer has a delay of 2 nanoseconds. So this means you see here the input B actually is changing somehow. The output X will follow the input. But again, be careful, because this inertial delay model has the, well, as the effect and the behavior that as soon as the input width of the input, the signal of the width of the input signal is smaller than the delay associated with this component. Okay, in this case 2 nanoseconds. If this is smaller, then this output will be suppressed. So this means there will not appear the output. So this is the standard behavior of all silicon components. So this is acceptable. If you would like to model silicon component, you have to use this inertial delay model. So in this case, we can do something like this. For example, if we would like to model maybe an output buffer outside of the FPGA. Again, remember, there's all components outside the FPGAs. And we would like maybe to model an AND gate which has a different low to high behavior compared to the high to low behavior. Then we can do something like this. First, we just model using a processor gate and an ideal AND gate without any delays. So this would be the ideal AND gate, producing the output signal in sync. Okay, so no delay at all, because as soon as A and B is changing, then the in sync will change. And then the next process actually is sensitive to the in sync. And now we analyze the change. Is this a change from 0 to 1, or is this maybe a change from 1 to 0? So we check this. In this case, we're asking for the final value, in this case 1. So this means it was a change from 0 to 1. Then we assign maybe from 0 to 1, the delay from 0 to 1. In this case, this is the time you defined here, TPH or TPD from low to high, in this case 3 nanoseconds, so it's faster. So, but if this is not the case, maybe it's the from 1 to low, then we assign the delay of 5 nanoseconds. So in this case, we really model the behavior of this, and this could be and this could be analyzed during your simulation because it might be connected to your FPGA. Okay, so this means that this would be the inertial model. But in some cases, we would like maybe to define another kind of delay model. It's called the transport delay model. So this is basically a cable. It's not a silicon component. It's a behavior of a cable. So in this case, we do have a component. Input is A, output is Z. So in this case, what happened is that all of the signals which are actually arriving at the input will appear after a certain delay on the output, but the signals are not suppressed or rejected, whatever. So this is basically the model of a cable, maybe a coax cable or just a delay line, because it's also part of your test bench, maybe. Okay. So now, in some cases, I would like maybe to use some variable delay. So let's assume we do have something like this. Again, I do have oh, something happened here now. Somebody maybe freed up the internet because now it's much better. So this again, my FPGA maybe here, okay? And I would like, and I have a connection maybe with this component. It's connected maybe with signal A, okay? And this is might be an external clock. So this clock will actually, trigger this external component, which is connected to my FPGA. Now, look to the datasheet of this component. The vendor of this component tells you if this is the clock, maybe here, then the output, let's say Q, then the output Q looks like this. It will change after minimum time. This would be the minimum, min. And there's a change will happen. But after, and this will repeat all the time again. So, but after the max time, the change is over. So this means it's the min, and that would be the max value here. Okay. So now, if I run the simulation, I would be interested to see all this, the situation, all the delay which are somewhere from min to max. So, but if I define just one value, 5, maybe here, whatever this is, then I just will run all the simulation with this one value, but I would like to cover all of them. So in this case, I would like to use random variable delays in the range from min to max. So in this case, the delay should be random as long as I run the simulation, maybe from min 2 up to 5 nanoseconds. Okay, then we can do something like this. So this is actually the recommendation of a function which define a variable delay. You define a function and you just as an input define an integer. It's the lower range. In this case, one would be the mean, and you define the next input. It's the upper range. Might be this one, and then inside the function you call this function called uniform, and this function uniform is part of the VHDL package mass underscore real. So this is part, so here we go, this is this package. So if you enable this package in your description, then you can access this uniform. And then this uniform returns to you a random value between 0.0 and 1.0. And then you basically multiply this, with min and max. And therefore, in this case, if you define maybe between min 2 and max is 5, then it will get all the value between 2 and 5. Okay, so this means as soon as you call this function, you will get a new random value, and this it's very, very nice because now you really can model the behavior of this component with a delay in this range. That's very nice. Just you use this and try this function in your design. Another very important stuff is the file I/O. Okay, file I/O. So what is the file I/O? Okay, let me just, I think now I can do it here a little bit better because somebody freed up all the internet stuff here. So I just go to my, my notepad here. Okay, let me just clear it up here. So why do we need a file IO? Well, actually two situations. First situation, I do have FPGA right here. Now, for some reason, I would like to run a simulation with some control file which controls maybe the input of some signals. So these are some signals, maybe very complex situation. So, but I don't have really a model for all the signals, but I can describe it using a text file. So this means using this text file, for example, stimuli, I can define a file, text file, and define the behavior of the signals. I can use the syntax. It's my choice. We'll see, it's my choice. And then inside the FPGA, we will actually analyze this and apply it to the stimuli. So this is for generating the stimuli. That's one situation. That's what would be the file input. On the other side, my FPGA is doing something. Maybe it's just generating from a block A some output. I would like to understand, is this correct or not? So I would like maybe to put, let's call it observer, to observe something. Let's call it observer. And I just take this observer and connect this maybe to this net. I would like to watch, to monitor, to generate a log file, and then just log all the information here, including time value and so on. So that's for the file output. So this means file IO. It's a very, very nice method to generate input files using a text file or generate input signals using a text file and monitor the behavior of the FPGA and generate log files for later analysis. So that's the whole situation here. So in this case, that would be the file IO. This means now, but in order to actually use the file IO, we have to, let's say, to enable this function. So in this case, that is the definition of the packages we need to make available to our in our description. It's a package text IO and a package standard logic text IO. We need two packages. Why two? Well, the first package is a text IO package, contains all the basic stuff like reading a line, writing a line, open a file, close the file, access the file, and so on. But the type standard logic, it's not a standard type in VHDL. It's this type standard logic is also an extra type which was added using an extra standard logic package. So in order to support this, so we need an extra package, and this extra package basically contains just all the procedures, reading and writing, but for the type standard logic. Because this package contains all the other types, the default types like time, integer, bit, string, and whatever. So that's the reason why we actually do need two kinds of packages. And these file operations actually are used to write test results to files, read test vectors from files, maybe read from keyboard. You can also connect your keyboard during simulation. And then the simulation will wait for the input from your keyboard. So in this case, you can do something, can define some interaction if you like, okay? And you can read and write ASCII file, text file, as well as binary files in different formats. So how to write text file? Well, that's actually very easy. First one, we have to define the packages. That's actually how we do this. Second, we have to, of course, declare the output file we would like to write. So in this case, file, log file, text, open, write mode, and then you set up the name. So in this case, I'm using the name log file text. And then we declare the line buffer, because you will see you usually never write directly to a file. You always first write to a line buffer, and then you just empty the line buffer to your actually to the file. So we have to declare the line buffer. We see the type of the line buffer is of type line, and then you actually write to the line buffer, and whenever you have defined your line buffer, the contents, you write it to the file called, this case, you writing to the line buffer is just a procedure write, and finally writing to the file is a procedure write line. So that's a mechanism how to do this. And here, an example here. For example, I would like to generate a log file. So I just define the log file. Okay, here we go. Then, because I defined the log file to open write mode, now what happens? If the file doesn't exist, it will be generated. If the file already exists, it will be cleared, deleted, and regenerated again. But you can also have, instead of using write mode, you can do append mode. So if you do an append mode, then you will actually open an existing file without actually deleting it. So in this case, you can add more information to the file if you open this not in the write mode, if you open this in the append mode. Now we define the variable, and now we get because we defined the line buffer, we got the empty. So this is the empty line buffer. Here we go. Now the next step. Let's assume I would like to write the timing information, not the time information for log, for a log entry. So in this case, the log file, the line buffer is log file line. So I write to the line buffer. It's a line buffer. Now is a keyword for the time, and this is the format. So this is write as arranged in the write. And the field is 10-bit, 10 positions. So in this case, it would be 10. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be, the field would be 10 characters in this case. Okay. So in this case, write. So in this case, write here. Maybe there's a time value written right here. Maybe, I don't know, 520 maybe nanoseconds, because it would be a blank here. Okay, so in this case would be a blank here, 52 nanoseconds, for example. Okay, so whatever. So and then, so this means you fill your line buffer. So in this case, you see, so in this one example here, my time at this time it was, the time value of 2024 nanoseconds as an example. Now I continue. Now I say H write, so this means hex write, because in this case you would like to print the address using the hex value. So this is the contents of this object. I would like to print the value. Again, the field size is 5, and the location is justification is or orientation is right. So in this case, it would be something like this. So in this case, the size of the address bus would be 16-bit. Okay, so these are 16-bit here because I'm using H write, and now the value would be written here. And you see what will happen, because I know these are 4 values here, but I'm using a 5 position field for 5 position. I automatically will get a blank here. So that is how you can do a very, very simple formatting of the output. And then maybe I would like write the data. So in this case, I'm not using a hex. I'm using maybe binary. And in this case, data would be maybe 4-bit. So then you will see again 4 bit binary data. Now let's assume the value is there, and now I say, okay, that's now should be written to the file, and then you say write line. So this means take the line buffer, here we go, and put it to the file which is actually defined here. So this is the handler log file, but pointing to this file. So if I do execute this, then this line buffer actually will be written to the file log file text. And this will be repeated all the time, because if you put this now in a process which is triggered all the time, okay, then will be repeated all the time, and it will then actually the file written. So very, very, very simple. Now, another example. So that's a very, very simple one. You see, I define maybe for, I don't know, just for showing you the idea. So I define again a text file lf, a log file for writing, and buffer for as a line buffer. And now I'm using also the attributes. And you see, if you do use a keyword and then you attach an attribute, tick simple name, this returns to you just the name. So in this case, write to the buffer. Now tick simple name returns to you now. So now you write now without the attribute. Now is the time. So in this case, now again, then you write this. Then you will see here the time. Okay, so in this case, you can even also define here the units. So in this case, nanoseconds. Okay, I think the default is picoseconds, but you can define the nanoseconds. Now they say that's it, and now you just write the file, the complete line to the files. Now you write the complete line to the file, and then you wait for 10 nanoseconds and you repeat all over and over again. So this is endless output, just to demonstrate to you how you can actually define and how can you actually set and do this kind of file IO. Now, how to read file? Well, that's actually the opposite. Well, we again first define the package. It's the same. Okay, now we have to declare the input file, which file to read. Okay. Again, we define the line buffer. This in this case called stimulus line, and then now we read. Now we read a complete line. So this is the opposite. Now we read the complete line, and then we empty the complete line by using a simple consecutive reads. So this means this is just the opposite to write. So for the write, we filled first the buffer and then we did the write line. For the read, we just do the opposite. We first read the complete line from file and then we empty this using the reads. Again, here an example. So that's actually the definition of the input file. Let's assume there's something in the file. That's actually written. This is maybe a time information here. That might be some name. That might be some other information. So you see, you will see right now, we really don't care about the syntax because we define our own syntax. Let's assume that's the contents. Okay. Now, how to read this? So first we define the stimulus line. Here we go. It's empty. Now we just have the next statement, read line. Okay, so read line. We read the complete line because we start reading. So the first line, the pointer points to the first line. That might be the first. Okay, here we go. So in this case, the contents of the stimulus line buffer would be the first line, 25 blank nanosecond blank Peter blank, and then 3387. And now you decide how to interpret the contents. For example, what you can do, you can say, well, the first entry is time, but this is just your choice. You could say, well, this might be the time value. So in this case, you read from the buffer. So this again, the buffer, this is the buffer here. But now that's the key point. You define an object time value, but the object time value is of type time. Because this of type time, the read procedure understands you're looking for time information. And then in this case, the time information consists out of an integer value and a valid time unit. So in this case, femtoseconds, nanoseconds, microseconds, seconds, minutes, and hours. So these are the valid timing, valid units of the time information. So in this case, it will found 25 nanoseconds, and the object time value will get the value 25 nanoseconds. And now the internal pointer is placed to this position, Peter, because this is already read. Now let's assume the next entry. I'm not finished, so I need to read more information. I just call read stimulus line string 1. So in this case, string 1 is, as the name of the object implies, is a character string. So this means the type is string. This means the procedure read expects a string, and the string actually is end with a blank. So this is a string. So in this case, the string 1 will have the the value Peter. Just be careful. If you use this as a string, then of course it's the delimiter. It ends here. But if you this blank here will be here because it starts here. Okay, so if you use a string, you will see the blank. Now, still not finished, and now I would like to read the last value. Now it's your choice. This could be the integer. So if you define the object to be integer, then the value would be 3,387. But you can also say this is a hex. So in this case, it would be a 16-bit vector with hex value 3387, 60-bit. Or it could be octal. So in this case, it would be 12-bit value, defined in an octal system. So you define how to read it. So in this case, I use integer. Now you will just read all the information here. Now we process the information, and then we read the next line. And so we are running the loop and read the next line. So that's what we do all the time. So this again, very, very simple example. I just that would be a file stimulus. It's just a timing information, nothing else. So I use maybe a text editor to do it. So then the file is defined here. The line buff is defined here. Now I start. While not end of file. So this is a keyword, end file. While not end of file loop. Read. First, we read a complete line. Here we go. Now we read first delay value. You see the delay values of type time. So this means we expect a type time. So delay value is here. Now we wait because of time. Now we wait for this time value. And now we just output O. Here we go. O. The toggling, the inverting. Okay. So after the time, the output will be inverted. So this would be really the output in a simulation of the output O. This means, after the time it gets even longer, because after 50 nanoseconds, you see, we just toggling the value. Very, very simple example. I do have another example a little bit later. I think I do have the time for doing this. So this would be the reading. And now some other general information about the stimulus and the very useful stuff when you run this test bench, when you define the test bench, what is nice to know and what is nice to have. First, how to define a simple continuous running clock. This means we do have In the test bench, you do an FPGA right here, and we do have maybe an oscillator right here, and we need to define this clock, okay? So in this case, you can do something like this. We define the signal clock, and define also initial value 0, and then maybe we define a constant clock period of type time. Then we say clock is not clock after clock period, half of them. So in this case, we will have a definition of a 100 megahertz 50-50 clock signal. Okay, you decide the 50-50, and that would be the clock. And maybe in order to define the reset, well, in this case, you define the reset, standard logic, and you can do in VHDL can do very simple. For example, this reset is 1, but it will be 0 after 27 nanoseconds. In this case, it will be after 27 nanoseconds. Usually, what we usually do, because we define the clock period here, we use also here maybe the clock period value in order to avoid, an unintended violation. But that would be how we can define the clock and the reset signal. So now this is a very simple stuff to define a clock with a ratio of 50-50. So in this case, what about if I don't have the 50-50? So non-50-50. So I can do this. For example, you can define a 60-40 clock. Say clock is 1 after the clock period 60%, when the clock 0 is, else it is 0 after clock period 40%. So in this case, there would be 60-40. Okay, or stop clock to 0 actually after all the stimulus applied. Stop clock. Clock is not clock after clock period, and so this is a standard definition, but only when done stimulus false, L0. This means if done stimulus is true, then the clock is 0 all the time. This means you can switch off the clock. The question is, you can switch off the clock depending on a signal, or you can switch off the clock depending on the time. Okay, clock is not clock, but only when now. Just remember, now is the time. When now less than simulation time, which is set somewhere. Okay, so the question is, why should what it should be interesting for me to actually stop the clock? Well, very nice. In this case, let's assume you do an FPGA, and that what is very, very typical, you have here a clock for the FPGA, okay? And inside the FPGA, everything actually is running with the clock in some cases, in a lot of cases. So, but if you so the clock is here, but now you stop the clock because all of the stimuli, you say that's okay. So in this case, if you stop the clock, the simulator understands there will never be a rising edge again. So the complete simulation will stop fully automatically. Instead of saying run for 20 or 30 microseconds, maybe you don't know how long, you can say simply run. It will stop automatically when you stop the clock. So that's the idea of why it's a good idea to stop the clock. Okay, and that will be in this case 90-degree shift for the clock, just to shift it, maybe to define some other specific things. So disable the clock again. Why is this good? So if you stop the clock, okay, then the simulation tool will tell you, oh, no more step vector to simulate the clock, because the clock is all the processes usually are triggered with a clock. So no, everything is done. So I have no input vectors to stimulate, so I stop. So that would be sometimes very, very interesting stuff for you. Or you can do something like this. You can define concurrent, asynchronous, or concurrent stimulus. What does it mean? So we define declare input data to be a 3-bit. Then you can do something like this. Input data is 0, 0, maybe, and then you use after, and then you define some initial pulse behavior here, and then it will stop. Okay, you can do this. The only thing what what you should be aware of, there's no relation to maybe the other clocks. Nothing is completely asynchronous. But maybe that's your intention. Then you can do this. The only information, the only important stuff is, so this must be the time here must also increase because it runs always of the time 00. So the time is actually, you know, counting up. Okay, so that's actually the one and only important stuff here. Or you can actually generate the stimuli, but it's controlled by time. So in this case, you say while now, again, now is the simulation time. Now I say, okay, while simulation time less than or equal to 100 milliseconds, then wait for some time and do something. So this means then for the time of 100 milliseconds, the time will change and then it will stay. Then will keep the last value because the loop is end, and then it will actually repeat it and comes back. Okay, so this means you can also control it by time, or you can actually so this part again, I go back. All of this stuff are asynchronous, no relations to the clock. It is possible, yes, but usually we do have some relation to the clock. So in this case, we can do something like this. We again set up a loop, but inside the loop we wait. So this means we do have a clock somewhere, and we wait for the rising edge. We wait always for this rising edge, rising edge, rising edge. Whenever it's a rising edge, we just change the data. So this means the data will change here. Okay, so completely synchronous. Okay, so in this case, we control this by a number, but it's actually asynchronous. That's actually very, very common. Very nice situation for running the simulation here. Okay, or of course again by time. Instead of having a number of synchronous applied vectors, we just limit this by time. You see, then for the time to 100 milliseconds, we do have a synchronous stimuli, then it stops, and then the clock runs. Anyway, it runs, but the value is constant. So this means it could be an initial pulse, initial pulses to be applied after power up, maybe, or something like this. Okay, so this is, sorry, 1 second. So this is actually for the control by time. Sometimes I would like actually to generate random data. It's also very important for me to generate random data. Random data, but there are several ways for you to generate random data. So in this case, it's very, very simple. Therefore, it's called simple. You just define a function and you just define some random constants, some constants. But you see that's not really random because you define some constants. Oh, sorry. It's here we go. So you define some random constants here. Now you can access this function random sample, and you will get some samples, but they are not really random because they may be random in a certain interval, but not really. Therefore, it's called simple. So it's not really useful. So maybe more complex, you just define LSFR. So this is a linear feedback shift register. Okay. So in this case, it's also used. It's also known as CRC generator. It's the same stuff. So you just take take a counter and then build using, there are a lot of information available in literature. Just build a shift register with linear feedback. Okay, so this means that you have a shift register right here. Sorry, my internet's again, something happened here. So, and then we have a shift register right here, you see. So, and linear feedback, this means we just, something happened here. So we just take the data here, maybe this one, and just having here an XOR. Difficult for me to draw because the internet is very slow, and then feed it back. Okay, so, and this means that if you look to the value here, then it looks like random. Of course, it's not random. It will repeat, depends on the size of shift register, but at least it's a little bit better than the simple random. And or you can define the grayscale data. You just again take a binary counter and just generating a grayscale pattern. So it's not, again, not really random, but it's not really 1, 2, 3, 4, 5. Okay, so it could also be some option for you. And what's actually the best what we can do is actually the uniform random. We know already this function, so we use already this function for the variable delay. So in this case, we define a function true random and define an input parameter integer, and then we call the uniform. Again, remember, uniform gives me back a random number between 0.0 and 1.0, and then it's basically will be multiplied by this num. So this means this is actually the range. So if the number is 10, you will get a random number between 0 and 10. If the number is 100, you will get the integer, the random number in the value from 0 to 100. So, and that's actually nice stuff to define and actually to run a simulation with random numbers of your FPGA. Okay. And that would be, that's again an example. We define this kind of the random, and then you just call it, you see, and then this again less, if the simulation time is less than 1 microsecond, we just generate a synchronous value because we are waiting for the rising edge, and then you see some kind of a random number here. So, and yeah, and that might be a good idea for us to run a simulation here. Okay. So now I actually prepared. Let me go back here. I actually prepared. I go back here for you. I have the time from the read file. So what I doing is something like this. Okay, so, and I hope so. I hope my internet is a little bit better. I don't know why, but it's very bad today. So what I would like to do is actually, it's bad again. I have some FPGA here, okay, and an FPGA. I do have some interface, and I would like maybe a very simple microcontroller interface, whatever. And I would like actually to simulate the microcontroller interface, by assigning some values. Okay, so in this case, I would maybe define the protocol. So I have here maybe the address, maybe something like this. So, okay, so these are invalid. So then maybe I have a chip select, and a chip select say, well, that's actually the access, and maybe I have read write. So for writing, I have maybe something like this, and I don't care here. And then write enable. That would be, yeah, the write impulse maybe here, and the data. So that's a simple microcontroller type interface, maybe something like this. So what will happen here is, that at this time here, to this address here, the data here are written. So that's a very standard microcontroller interface. The point is, I don't like in this case maybe to really because it's actually easy, but I would like to actually to make it to demonstrate to you the file IO. So what I'm just going to do, I just use file IO here to describe the model of this external microcontroller. Okay, and I just did it a very simple design, and I show it to you. So the design is called simple interface. And that's what I just defined. Is actually, you see, address, data, bidirectional data bus, chip select, write enable, read write, and output enable. And internally, I have the definition of a RAM. It's a 256 by 8 register set internally. Yeah? And then I just define writing. I say, okay, if there's a write impulse, write enable, and chip select is set, and read write is also set, then please go ahead and write to the data. But if you would like to read the data, you see data is a bidirectional. Here we go. Here, by in out. So, but if this is a bidirection, then read the data, and when it's read, when chip select is 0, read write is 1, and output enable is 0, then you can output the data to read. And if this is not the case, then it's high impedance because it's bidirectional. So that's actually basically the very simple interface. Now I define a test bench. So in the test bench, I just have here the declaration of the component. Here we go. Then, of course, the declaration of the signal. That's the instantiation. And here, to make it simple, of course, usually I would put this in a separate, let's say, component called host, microcontroller, whatever. But I just defined, to keep it simple here, just a process. And what is the process doing? Well, the process actually is starting and reading the file called, and the file is located here, host.txt. And this file, host.txt, contains instruction which are executed by the microcontroller, like reading and writing memory locations. Okay, so and I define it here, and now it starts here. And while not enter file, then go ahead, read. Is this a read or write? If this is a read, then read the address, wait for 10 nanoseconds, define the chip select, define the output enable with reading, and set the read and write signal, wait for 40 nanoseconds, and then deactivate all the signals and go and read the next value. But if this is all right, then read the address, read the data, and then activate the chip select. No output enable because we are writing, set the write inputs to 0, write the data, and write and take the write stroke. Okay, and then again, just go back. And if you have another other signals, then just read the next line without doing something. So now let me check the contents of this file, because this is the file is okay. There's the file. 1 second. And temp host text. Okay, so temp. Okay, temp here text. Okay, now if I just open this, here you go. Here you go. You see, very simple one. That's comment, read address, return the data, and write address data is a write access. And now I'm reading the address 12. Now I'm writing address 1256. I'm writing 40. This is the hex addresses. These are the hex data. Then I'm reading back the values. Very, very simple stuff. You see, this are just few line of codes. Okay, so it's very simple. This means now I can actually run the simulation by just calling the simulator here. I don't know. Okay, save. I don't. Now it's just takes so long. I don't know. It's a mess today here. So now should be takes a little bit. Sorry. What happened? I have some problem with my setup here. So I can well, I can do it here. But what happened with my okay, yeah, this is it. Yeah. Okay. I don't know, sorry, but I would like to show you to you. So let me close this and then reopen this again, because something happened and I don't really understand what today is a little bit. I don't know what happened today with my laptop here. Sorry. So now I just close this one and I just again open this, and then maybe it will come here. I would be happy to see you again in our next webinars. And I will send also to you the example I prepared here. Sorry, I was not able to run it because something happened with my Vivado. I need to reboot all my computer. I don't know what happened, but I will also resend it to you. Okay, so thank you very much for your attention and see you next time. Okay, goodbye.